All right, so we're going to look at this transformer example. What I've got here is a source, Vs, which is 25 kV with an angle of 0, which is sending power to a load, and that load is on the secondary of an ideal transformer. So what I have is a pretty typical power systems type of problem where I have a source, Vs. I have it transmitting power, right? So I guess it's sourcing power, Vs is sourcing power to the load through this transformer. So the source is connected to the transformer through a transmission line, which has some resistance and some inductance. And in this case, what I have with my transformer is I have the polarities flipped on this transformer. All right. So to approach this, I'm going to approach it two ways. First, I'm going to approach it the way I like to approach it, which is to set up the polarities the way that I like the polarities to be set up. And then I'm going to repeat the problem assuming that I've been told what the polarities need to be, and I just have to deal with it. Okay. So if I deal with it the way I like to deal with it, then what I say is I put the plus signs at the dots, like so. All right, so V1 goes plus to minus, V2 goes minus to plus. And I like to put a current I1 flowing into the dot on the primary and my current I2 flowing out of the dot on the secondary. Now, why do I like that? Because I know what's going on in this problem. What I know is going on is I have a source that's providing power to a load. So essentially what's going on is whatever power is flowing out of this source flows into the primary, is absorbed by the primary, and then is sourced by the secondary into this load. That's the way I like to approach it, at least. And when I do that, I think of the problem like this. The thing I always remember is the magnitude of the voltage phasor on the primary over the number of turns on the primary is equal to the magnitude of the voltage on the secondary divided by N2. All right, this is always true. No matter how I set up the polarities, this is always true. Okay. Now, in this particular case, V1 over N1 equals V2 over N2. Okay. This is true when both plus signs are at the same spot. Okay. Either both at the dot or both not at the dot. You might ask, well, why do we ever even play around with this to begin with? There are times when I want to make a phase change that go across the transformer. All right, there are reasons why I might want to do this, so we need to be able to think of it both ways. All right, I like to set it up this way just again because I know what's happening is I am sourcing power out of this guy, absorbing it into the primary, and then what's happening on the secondary is it is sourcing it out. Now, the way that I remember the current relationship is I say because the transformer is ideal, because it's ideal, energy, meaning power, is always conserved. Okay. Now I sometimes state that as power 1 equals power out, but really what that means is that power 1 plus power 2 equals 0. All right, and I could do that if I wanted to also for S1 plus S2. All right, but it's easiest to just think in terms of regular powers. Okay, so the two powers have to be equal to each other. All right, and if you look at it, what ultimately ends up having to be true is that the power factors are the same. All right, so that essentially what ends up happening, if the power factors end up being the same, I get that in this case, P1 is V1, I1. There would be a power factor angle, but if they're both the same, then it drops out. okay, V1, I1. And because on the other side, if you look here, right, on the primary side I have a current flowing in, so I write that power positive. On the secondary, I have a current flowing out of the plus sign, so I wrote that as a negative. It's sourcing power, so minus V2 I2 equals 0. So if I look at this, I get V1 I1 equals V2 I2. Again, I could have written in the power factor on both sides, but it's not hard to show that power factor in the case of this transformer. The power factor on the primary side and the secondary side would be the same. Okay, it has to be. That is not true in general, okay, if I were looking at loads, right? But on the both sides of the transformer, the power factor ends up being the same. So what I then end up doing is I combine this fact with what I know about the voltage relationships. So I will say that in this case, V1 is N2 over N1 times V2 I1 equals V2 I2. So I substituted in the voltage relationship. The V2's cancel, and I get that N2 over N1 I1 equals I2. Okay? Now this is true in this particular case. All right? I need to think about it in the other cases, right? But I can always derive it from this power relationship. This statement, always true. Always true. So the two statements here that are always true, I've put in the boxes. Okay? Those are always true. Then we need to play with the signs, all right? This guy, I just play with the signs by looking at where the polarities are. And then this guy, I look at the signs by looking at whether I have power flowing into one side or flowing out. Okay? And we'll look at that, when we solve this problem a different way in a little while. All right, so knowing the relationships that we're going to use here, so this one and this one here are the two that we're going to use. Okay, all right, so how do I solve this problem? And what am I even looking for to begin with? Well, what I want to know is I1, I2, and V2. Okay, I want to solve for those terms. So here's how we approach this. So the first thing I do is I do KVL on the primary. Okay. So 0 equals, I do my KVLs always the same way. I start down here and I work myself around in a clockwise direction back to where I started. All right, and if I'm going to do this, I like to define my polarities. So I'm going to define a polarity there, okay, on that impedance. So I have a voltage drop across the transmission line impedance. And then on the secondary side, I'm going to say, let's see, I go plus to minus. Because I have a current flowing into the load here, I'll do plus minus, and then plus minus like that. Okay. All right, so on the primary, I start in the bottom corner, and I go in a clockwise direction. So 0 equals minus Vs plus I1 times 1.5 k ohms plus J times 6 k ohms plus V1. Okay, so I can bring the Vs over and I have this. All right, now the problem is, oops. All right. All right. The problem I have here is I have one equation, I guess, and two unknowns. I don't know I1, I don't know V1, but I have my transformer relationships, right? I know that V1 over N1 equals V2 over N2. So in this particular case, I see that N1 is 25 and N2 is 1. So that means that I have V1 over 25 equals V2 over 1. Now, like I said in class, that doesn't mean the primary side has 25 turns and the secondary has 1. It just means that the primary has 25 times as many turns. All right, that's one turn doesn't usually cut it. All right, so I can say that V2 equals 25 V2 equals V1. Okay, and I can plug that into here. To do that, I need to get some relationship for V2. So now I do KVL on the secondary. Okay. So I did my KVL on the primary, now I'm going to do KVL on the secondary. So let's look at that. If I go again around in that clockwise direction, okay, I'm going to start here in the bottom, go around clockwise. So I say 0 equals, first thing I'm going to do is go through the load. So I'm going to say 0 equals I2 times negative J 14.4 plus 4. All right, that guy was 4 ohms. All right, and then I go minus the plus through my secondary. So I say minus V2. Okay, so I say V2 equals I2 times negative J 14.4 plus 4. All right, now I know that essentially that 25 times this is equal to V1. So V1 would be equal to 25, multiply this whole thing by 25, like that. Now, I could bring that in, so then combine, and I could say Vs, so I'm combining this equation with this equation, and I get Vs equals I1 times 1.5 k ohms plus J times 6 k ohms plus 25 I2 times negative J 14.4 plus 4, like that. Now, the problem is I still have two unknowns, right? I have I1 and I2, but I can relate those to each other as well, right? I know that, so N2 over N1, this relationship over here, N2 over N1, I1 equals I2. In this case, I have 25 I1 equals I2, okay? So I again plug that in, and I get Vs equals I1 times 1.5 k ohms plus J times 6 k ohms plus 25 squared I1 is negative J 14.4 plus 4. Now this 25 squared, the fact that I just had the turns ratio squared appear in here is important. If you look at this, we're going to come back to this term for a second, but there's something that just happened there that we're going to make use of later on to sort of simplify this stuff. Okay. All right, now looking at this though, clearly what I have is one unknown, I1, and I can solve. So to solve that, I actually wrote for myself a little MATLAB program. Okay. So here is the MATLAB program I wrote. Okay. So I put in VS, I put in R1, X1. So X1 is what I call the impedance, the reactive impedance of my inductor. Okay. We tend to refer to that as X when it's a reactive term. Then I have R2 is 4, X2 is negative J times 14.4, and then I have my turns ratio. I've just called that N, right? So in this case, what I've said is that N equals N1 over N2. All right, that's 25. Okay. So then I solve for I1, right? If you look at this equation, Vs over R1 x1 plus n squared times x2 plus R2, if you look at that carefully, that is this equation right here, okay? So I solve for I1, then I solve for I2, then I solve for V2, okay? So let's do that. Let's take those terms. What I do is I copy and paste those over into MATLAB, run it, okay, and I get a couple of different answers. So what I'm going to particularly pull out here is I had it tell me the magnitude of I2, the angle of I2, the magnitude of V2, and the angle of V2. So let's write down what those are. So it looks like what I got for I2 was 125 amps magnitude. And my angle looks like it's 36.87 degrees. And for V2, looks like I got 1,868 with an angle of negative 37.61 degrees. Okay, so if I draw my phasor for that, right, this would be my I2, and then my V2, the negative 37 degrees would be somewhere down here and a lot bigger, right? This would be my V2, like that. Let's get rid of that part of the arrow right there. Okay. All right. So in this case, I would say that I2 is leading, right? I2 leads. That's not surprising, right? Because what do we have? We have a capacitive load. So with a capacitive load, I would expect my current to be leading, okay? So not surprising there. Now, that's what I get if I approach the problem by setting the polarities the way I wanted to, all right? Now I'm going to try to approach this problem a different way, okay? So this is the problem I actually took from another textbook, the original problem, okay? So you can see all the component values here are the same, okay? The big difference is they've told me the polarity of V2 is flipped, okay? And they've told me the polarity of I2 is flipped, right? So I2 is actually flowing into the dot over here, all right? Otherwise, everything's the same. I still have Vs equal to 25 kV with a 0-degree angle, okay? So what did we say was always true? The two things I said was always true, V1 over N1 magnitude equals V2 magnitude over N2. Always true. Also always true that P1 plus P2 equals 0. Those are our two truths. All right. Given the arrangement here that the plus signs are reversed, one is at the dot, one is not at the dot, I have V1 over N1 equals negative V2 over N2. In other words, there has to be a sign reversal. Or basically what that says when I have a negative sign is I have a 180-degree phase change between V1 and V2. Now, looking at the powers, okay, I see that P1 equals V1 I1. Again, there would be a power factor, but in this relationship up here, the power factor is always going to be the same for the two sides. Okay. P2, in this case, so I wrote P1 as positive because I1 was flowing into the plus sign. On the secondary side, I have a current flowing out of the plus sign. So I have this is negative V1 I1 or sorry, negative V2 I2, right? Because the current's flowing out like that, okay? All right, so what does that tell me? So I have V1 I1 minus V2 I2 equals 0. So V1 I1 equals V2 I2, okay? Now, I could essentially plug in this relationship here, and what that's going to end up giving me, same basic relationship I had before, which is that I1 equals now negative N2 over N1 over I2. So notice that a negative sign has appeared here and there, okay? One thing I can also always add to my truths, I guess, is that the magnitude of I1 equals N2 over N1 times the magnitude of I2, okay? So I sort of recommend saying that these are the three things you should really remember about transformers. And knowing those three things, you can always be able to figure out the polarities, okay? The other thing I guess you need to know is how to figure out whether or not these powers are positive or negative, right? From there, you can figure out pretty much everything. All right, knowing all that, let's approach this problem knowing we are going to use this relationship and that relationship, okay? So, in this case, same thing. So KVL1, KVL, KVL1 is 0 equal minus Vs. All right, let me, probably should do my polarities again. Plus minus here. All right, for the voltage across that transmission line. On my load, given that the current's different now, I'm going to do my polarity like that, okay? That way I have current flowing into the plus sign. So going around clockwise, so going minus Vs plus I1 times the 1.5 k ohm plus J times 6 k ohms plus V1. And then I have my KVL2. Okay, my KVL2, which is basically now, if I go again clockwise on the secondary side, I get the same relationship as before. 0 equals minus V2. So now I go minus to plus. All right, then I go plus to minus. So I say plus I2 times 4 minus J 14.4, like that. So V2 equals I2 times 4 minus J 14.4. Okay. And what do I know? What do I know? Well, in this case, I know that V1 equals negative N1 over N2 times V2. So then negative 25 V2. So I know that V1 equals minus 25 I2, 4 minus J 14.4. Okay, so all I did here was I took this guy, used it with that. All right, now I've got a negative sign. Previously I didn't. Okay, so this can be combined into there. All right, so I can say that Vs has to be equal to I1 times 1.5 k ohms plus J times 6 k ohms minus 25 I2, 4 minus J 14.4, like that. Now, what do I do next? Well, again, now I've got two currents in there, just like I did before. I don't like that. I want to get one current, then I can solve it. All right, what do I know? Well, I know that I2 has to be equal to negative N1 over N2 times I1 right? Right. And I know that I1 has to be equal to negative N2 over N1 times I1, sorry, times I2, okay? So I can use those facts here, okay? All right, so I'm going to use this first fact here to say this is negative 25 I1. And I'm going to say, I'm going to plug in I2 equals negative 25 I1 into here. So I get Vs equals I1 times 1.5 k ohms plus J times 6 k ohms plus 25 squared I2 times 4 minus J, 14.4. Now if you look, this equation right here that I just wrote is the exact same one that I wrote previously, right? The exact same equation. That's not surprising because I haven't changed anything about the primary, okay? I haven't changed anything about the primary, so I kind of expect that's the case. The only thing I've changed is on the secondary side. Because I've changed the secondary side, I'm going to end up changing some things about that. But I haven't changed anything about the primary. Okay. So now let's try to solve this guy again. So I'm going to look at my MATLAB code. Here's my second version. All right, I'm solving for I1, 2, and I solve the same equation. In this case, however, I say that I2 equals negative 25 times I1, and then I solve for my V2 using the current that I got. So let's plug this in. Okay. Let's look at our results here. So my I2 is equal to 125, which is the same magnitude I had before, but what I have is an angle of 143.13, and my V2 has the same magnitude, 1868, and has an angle of 142.39 degrees. Okay, so if I draw those, all right, what I end up finding out is that I get in each I2 is over here, V2 is over here. Okay, now if I compare that to what I showed here, okay, let's see if I can copy this. Let's see if this will work. Looks like I can. All right. So if you look at what happened, here's V2 over here, here's V2 here. This was method 1, right? Where I determined the polarities myself. This is method 2. Notice that what's happened is that in the two cases, so as I went from if I look at the V2 here and the V2 here, I can see that they're separated by 180 degrees. Look at the I2 here and the I2 here, they're separated by 180 degrees. What is 180 degrees equal to? Well, remember, 180 degree shift is the same as multiplying by -1. If I take I times -1, this is the same as taking I and multiplying it by e to the j 180 degrees. Okay? So it's a 180 degree shift, right? Right? Go through the math, right? If I say e to the j 180, right? That's cosine 180. plus j sine 180, which is minus 1. Okay, so this guy is equal to, so you should be able to see that those are equal. And so if I look at the expression that way, I know that the angle of I plus 180 degrees is the angle of this result, right? So if I take V2 and I multiply it by minus 1, this angle changes by 180 degrees. I'm going to take this guy and move him back here. If I take I2 and multiply him by 180 degrees, I'm going to rotate him back around 180, and he's going to be pointing back this way. Same as multiplying him by minus 1. So it kind of makes sense that I get that minus 1 result, because if you look here, the polarity is flipped. If the polarity is flipped, then my answers become negative, right? The way that that manifests with phasors is to say that my angles shift by 180 degrees. A 180 degree shift in angle is the same as a minus 1. All right, what's the important thing here? The important thing is really that you remember these three relationships. The magnitude of V1 over N1 is the magnitude of V2 over N2. P1 plus P2 equals 0. Magnitude of I1 equals N2 over N1 times I2. I look at it this way. I know these relationships. I say that if my plus signs are both at the dot, then my voltage relationship becomes positive. If I have them mixed like this, where I have a plus sign at the dot and a plus sign not at the dot, then I put a negative in this relationship. And then for my power relationship, I just look to say, well, the power is positive on this side because I have a current flowing into the plus sign. On this side, I say that it's negative because I have a current flowing out of the plus sign, right? That's the way we define power. That gives me the sign of my current relationship, okay? All right, so hopefully that example helps a little bit.